Let's get back to work. Module 2, Session 2.3. Now let's discuss parallel RLC circuits. A parallel RLC circuit consists of a resistor, inductor, and capacitor connected in a parallel circuit which is powered by an AC source with a particular frequency. As with a series RLC circuit, the current and voltage will be out of phase between 0 and 90 degrees, depending on the values of these components. Please note the following. In a series RLC circuit, the supply voltage is equal to the phasor sum of all the voltage drops across each component. The current flowing through the circuit is the same throughout the circuit. In a parallel RLC circuit, the total current is the phasor sum of the current flow through each component. The supply voltage is the same across each component in the circuit. Let's do an example. A 50 ohm resistor, a 20 millihenry inductor, and a 5 microfarad capacitor are connected in parallel across a 50 volt 100 Hz supply. Take 5 minutes to draw the circuit diagram. Your circuit diagram should look something like this. Let's do some calculations. You are asked to calculate the following: the current flow through each component, the total current drawn from supply, the total impedance of circuit, and the phase angle. Take a few minutes now to do these calculations yourself. Then we will go through the solutions together. Before you can calculate the current flow through each component, you need to calculate the values of inductive reactance XL and capacitive reactance XC. To calculate XL, we use the formula XL equals 2 pi FL. So XL is equal to 2 pi multiplied by the frequency, which was given as 100 Hz, multiplied by the inductance, which is 20 millihenries. Remember that to use this formula, inductance must be in henries, so we need to convert 20 millihenry to henries and write it as 20 multiplied by 10 to the power of -3 in our calculations. Type all the values into your calculator and you should get a value of 12,566 ohms. This is the inductive reactance which we will need to calculate the current flowing through the inductor. Now let's calculate XC, the capacitive reactance, using the formula XC equals 1 over 2 pi FC, where F is the frequency in Hertz and C is the value of the capacitor in farads. Substitute our known values, remembering again that we need to convert our capacitance value from microfarads to farads. You should get an answer of 318,31 ohms. Now that we know these values, we can answer our first question, which was to calculate the current flow through each component. Let's remind ourselves of what the circuit diagram looks like. How do we calculate the current flowing through the resistor? We use Ohm's law. The current through a component is equal to the voltage divided by the resistance. So, IR is equal to V over R, which is equal to 50 volts over 50 ohms, which of course is equal to 1 amp. Therefore, the current flowing through the resistor is 1 amp. Let's now calculate IL, the current flowing through the inductor. For this calculation, we still use Ohm's law, but instead of resistance, we use the inductive reactance, XL, which we calculated earlier. Inductive reactance is basically the resistance through the inductor. So, IL is equal to V over XL, which is equal to 50 volts divided by 12,566 ohms. Your answer should therefore be 3,979 amps. We calculate IC in exactly the same way, using the capacitive reactance as the resistance value. IC is equal to V divided by XC, which is equal to 50 volts divided by 318,31 ohms. Your answer for the current flowing through the capacitor is therefore 0,157 amps. The next question asked us to calculate the total current drawn from the supply. In a parallel arrangement, the total current is the phasor sum of the current flow through each component. We therefore use this formula. The total current is 3,951 amps. Let's now calculate the total impedance of the circuit. Because this is a parallel circuit, you should have used this formula for your calculations. Z equals V over IT. It gives you an answer of 12,655 ohms. The final thing we are asked to calculate is the phase angle. Using the formula theta equals cos to the power of -1, open brackets, IR over IT, close brackets. We get an answer of 73,34 degrees. In a parallel circuit, the inductor, capacitor, and resistor will always occupy specific positions in a phasor or vector diagram. Remember that the current divides through each branch of the circuit, but the voltage is the same across each component. For a current phasor, if IC is greater than IL, then the total current phasor IT will tend towards IC. If IL is greater than IC, then the total current phasor IT will tend towards IL. The impedance for a parallel resonant circuit is purely resistive and at a maximum. The resultant current is therefore at a minimum. This is referred to as the dynamic impedance and is represented by the formula ZD equals L over RC. That brings us to the end of Module 2 on RLC circuits. In the next module, we will discuss the all-important concept of resonance.